In this video, we will continue our investigation into power series. Recall, a power series is a series of the form given here, where x is a variable and the c sub n's we refer to as the coefficients. Also recall that we can think of this power series as being a function. We'll call it s of x for the sum of the series. And the first big question we want to answer is, what is the domain of this function s? Stated differently, what are the values of x for which the given power series will converge? Now in our previous video we discussed power series precisely of the form above, which we will refer to as a power series centered at 0. But more generally, instead of having an x in our power series, we can replace that with an x minus a and refer to this as being a power series centered at a. And this question still remains, given such a power series, what are the values of x for which the power series will converge? And it turns out that regardless of the power series we are given, there will always be exactly 3 possibilities. And the 3 possibilities are as follows. For a power series centered at a, the power series will only converge at x equals a, that is the value where it is centered, or, as we saw in a previous example, the power series will converge for all values of x. And then the third possibility, somewhere in between, is that there is a positive number r such that the series converges if the absolute value of x minus a is less than r and diverges if it's bigger than r. And just to make an observation, let's note that x minus a, an absolute value less than r, is equivalent to saying that x minus a is bigger than minus r and smaller than r. And we can add a to each part of this inequality to write it as a minus r is less than x is less than a plus r. And this is really describing for us an interval. It's telling us that x is in the interval going from a minus r to a plus r. And this interval is typically going to be referred to as the convergence set of the power series. And this value that we have, big R, is going to be referred to as the radius of convergence of the power series. And in each of the 3 possibilities, there is an associated radius of convergence. If the series only converges at x equals a, we would say the radius of convergence is 0. And if the series converges for all possible values of x, we would say the radius of convergence is infinity. Furthermore, one important observation that we need to make. When we come up with this convergence set, which we are going to use the ratio test to determine, this is where we are guaranteed that we have convergence, but there are 2 points in particular that we need to check. We need to check the endpoints a minus r and a plus r. So we always need to check the endpoints. And we will check the endpoints individually by plugging those specific x values back into the power series and then going back to our previous convergence test to determine whether that given series converges or diverges. So let's explore a few such examples. Let's determine the convergence set for the given power series. And note, because of the x minus 1 to the nth power, the language we would use here is that this is a power series centered at 1. So to find the convergence set, we are going to use, once again, the ratio test. So we need to take the limit as n approaches infinity of the absolute value of an plus 1 all over a sub n. And recall that a sub n is the quantity being summed by the series. So to form a sub n plus 1, for each n, we replace it with an n plus 1. So that would be x minus 1 to the n plus 1 over n plus 1 squared. So n plus 2 squared. And instead of dividing by a sub n, we are going to multiply by its reciprocal. And then, as we've seen previously, we simplify. The x minus 1 to the n in the denominator cancel off n of the x minus 1's in the numerator. In fact, there's only one x minus 1 left, and that's the only quantity present that requires absolute values. We will go ahead and pull that x minus 1 out in front of the limit, and what remains would be the limit as n approaches infinity of n plus 1 squared over n plus 2 squared, which we will conveniently express as n plus 1 over n plus 2 quantity squared. At this point, thinking about taking the limit and plugging it inside the square, we would be taking the limit of a degree 1 over a degree 1, which means we simply divide their leading coefficients. So what we are left with is the absolute value of x minus 1 times 1. And by the ratio test, this will converge as long as it's smaller than 1. So equivalently, we can say minus 1 is less than x minus 1 is less than 1. Adding 1 to both sides yields that 0 is less than x is less than 2. So at this point, we can immediately determine what the radius of convergence is. That would be the r value given here. So our radius of convergence, r, is equal to 1. And we mostly have the convergence set, but what we need to do is check the 0 and the 2. Note when x is equal to 0 or x is equal to 2, the limit that we have evaluated ends up being 1, so the ratio test is inconclusive. This is the reason that we always have to check those endpoints. So when x is equal to 0, so go back to our original series and plug in x equals 0. We would have the sum from n equals 0 to infinity minus 1 to the n over n plus 1 squared. This is an alternating series, and I'm going to leave a few of the details to you, but it will converge by the alternating series test. And if necessary, you should be able to go through those previous details. The second endpoint, x equals 2. When we go back to our original series and we replace x with 2, 2 minus 1 is 1, 1 to the n is 1. So this would be the sum from n equals 0 to infinity of 1 over n plus 1 squared. And once again, leaving a few details to you, this will converge by the comparison test. So putting this all together, we know the series converges at 0, 2, and from 0 to 2. So the convergence set is going to be the closed interval from 0 to 2. And just as a recap, this is a very typical example. We want to know the convergence set, so we apply the ratio test. Along the way, we will get that radius of convergence, but once we have the interval determined by the ratio test, we always need to go back and check the endpoints individually for convergence using our previous convergence tests. In this example, we will determine the convergence set of the given power series. And note, because of the form x to the n, we would refer to this as being a power series centered at 0. So once again, we will use the ratio test. We think of whatever we are summing as being our a sub n, and to apply the ratio test, we need to calculate the limit as n approaches infinity of the absolute value of an plus 1 over a sub n. So it's a limit as n approaches infinity, a sub n plus 1 would be x to the n plus 1 over n plus 1 plus 1, so that would be n plus 2, and then 2 raised to the n plus 1 power. And instead of dividing by a sub n, we multiply by its reciprocal, n plus 1, 2 to the n, all over x to the n. And now we perform a few very basic simplifications that are hopefully becoming quite familiar. X to the n cancels off n of the x's, which appear in the numerator, and we can go ahead and take that remaining x, which will be an absolute value, and pull it out front of the limit. Furthermore, the n2's in the top cancel off with n of the 2's in the bottom, leaving us with a single 2, which pulls out as a 1/2. And what we are left calculating the limit of would be n plus 1 over n plus 2. And since this is already a positive quantity, we no longer need the absolute values. The limit is of a degree 1 over degree 1, dividing their leading coefficients. That limit is 1, so we are simply left with absolute value of x less than 2. By the ratio test, we are guaranteed convergence as long as this limit is less than 1. That would be as long as the absolute value of x is less than 2. And this is the point of the problem where we have determined the radius of convergence. So r is equal to 2. Rewriting without the absolute value, we have minus 2 less than x less than 2. So to have the convergence set, we need to check each of the endpoints individually. So for that left endpoint, x equals minus 2. If we look above, if we replace the x we see with a minus 2, this will be the sum from n equals 0 to infinity of minus 2 to the n over n plus 1, 2 to the n. And a minus 2 to the n divided by 2 to the n almost cancel with each other. What it leaves would be a minus 1 to the n in the numerator. And this is all over n plus 1. This is an alternating series, and it will converge by the alternating series test. Similarly, for x equals 2, we replace x with a 2. When you plug in x equals 2, you have 2 to the n in the top, 2 to the n in the bottom. Very conveniently, they cancel. And what we're left with is the sum from n equals 0 to infinity of 1 over n plus 1. And thinking back to our familiar tests, this will diverge. We would like to use a comparison test, but as you can check, the inequality does not work out correctly, so we have to move on and use the limit comparison test. So now we know exactly what our convergence set will be. We converge at minus 2 all the way up to, but not including, 2. Written as an interval, that would be minus 2 with a closed bracket to an open bracket at 2.